So in section 11.4 and 11.5, what we're going to do now is we're going to take this idea of permutation and combination, and we're going to see how we're going to use it to help us compute different probabilities. Now, when you're looking for probabilities, it's just part out of total, where the total is the total sample space. So it's that total number of committees. You know, what are the chances, say Sally and Fred are in the committee, or what are the chances of getting both of them on there? So that would be, you would have to look at all your different permutations and count how many you have with just Sally and Fred and divide that by the total number. Okay, that's a probability. So the formula is a little bit scary, but if you have an event, something that you want to do with equally likely outcomes and a sample space that also has equally likely outcomes, then the theoretical probability of the event occurring is just the number of outcomes in the event divided by the total number of possible outcomes. That's the formula for probability. And we'll look at some examples, and I think it's going to make sense to you. So this is from your homework. It says we have a 12-sided die. Have you ever seen those die with lots of sides? Okay. It says the set of equally likely outcomes, meaning if you roll it, it's not an unfair die in any way. You roll it, and any number is likely to come up on any of the 12 sides. So you have 12 different outcomes. That's the total sample space. When you roll it, you have one of 12 numbers is going to come out. So the probability that you roll a 6, well, since there's only one 6 on one side, it's just going to be 1 out of the 12 possible outcomes. So the event there is to roll a 6. There's only one way for that to happen. The total number of outcomes possible are the 12 different sides of the die. Okay, so that's this idea. But probably it may be a little bit intuitive to you. All right, so then the next question, or the next few questions on your homework, I kind of skipped because there were quite a few, and this is kind of repeats, so I didn't look at too many of them. But for the next few examples, we need to consider a deck of cards, which unfortunately nowadays people aren't as familiar with cards. I guess it's because we play other types of games, video games and such, so we don't play with cards as much. But a standard deck of cards has 52 total cards, and it's made up of 4 suits. And each suit is denoted by a particular shape, either a heart, a club, a diamond, or a spade. And the hearts and the diamonds are red, and the clubs and the spades are black. And within each suit, you have the same 13 cards. You have, meaning there's an ace of hearts, an ace of clubs, an ace of diamonds, an ace of spades. And so these range from ace to king. It depends on the game, but a lot of times an ace is a 1. And so it can be 2, 3, 4, 5, ace, and then 2 to 10. And then jack, queen, king, where the jack is like an 11, the queen is like I don't know. If you're playing blackjack, I guess it's different, isn't it?
It's 10.
There are 10. We're not playing blackjack. But anyway, so here's some cards, and this is the idea, what they look like. They do call the jack, the queen, and the king either picture cards or face cards, and the A, of course, is the ace. So if you're dealt one card from a standard 52-card deck, what is the probability that you're dealt a 3? Well, how many different 3s are there in a deck of cards? 4. So the probability is 4 out of 52. Now, your answer has to be reduced. So 4 actually divides into both 4 and 52. 4 goes into 52 13 times. It goes into itself 1 time. If you're having trouble remembering how to reduce fractions, your calculator can be used as a tool. If you do 4 divided by 52 and then hit enter, then you can use the math button and then to a fraction, which is choice 1, and then hit enter again, and it'll give you the reduced fraction. So that's kind of a fun feature on your calculator. All right, well, what's the probability? Now, here's the next question. You're dealt one card from a standard 52-card deck. What's the probability of being dealt a heart?
13 out of 52.
Good. There are 13 hearts, and there are 52 total. And 13 divides into 52 4 times, so this is 1/4. But you could do that with your calculator. You could do 13 divided by 52, and then do math frac if you don't know that 0.25 is 1/4. All right, now we want the probability of being dealt the queen of diamonds.
1 in 52.
There's only one queen of diamonds, 1 out of 52. Okay. Now for the next few problems, they actually give you the sample space. But towards the end, we're going to recognize that we could have computed this sample space or the number in the sample space with our permutation formula that we have. Now they tell you a fair coin is tossed 3 times in succession. The set of equally likely outcomes is all heads, 2 heads and a tail, head, head, tail, head, tail, head, tail, head, 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 tail, 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 head, tail, 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 head, and tail, tail, tail. Right? Those are all the different things that could come out. Now I ask you this: is this a set of permutations or a set of combinations?
That would be
Good. Those are permutations. Because notice, here's 2 heads and a tail. Well, here's 2 heads and a tail. But order matters, right? When you're flipping, or in this situation. Okay. So your sample space consists of 1, 2, 3, 4, 5, 6, 7, 8. And if you wanted, you could think of it, so we have, is that right? 1, 2, 3, 4, 5, 6, 7, 8 in our sample space. So if we want to find the probability of getting exactly 2 heads, all we have to do is count how many of these have 2 heads in them. Here's one, right? Here's another, and here's another, right? So 2 heads is.
you're going the wrong way. You got failed.
I was just checking to see if you guys are getting. Just kidding. All right. Here's 2 heads. Here's 2 heads, and here's 2 heads. You like that better?
There you go.
All right. Okay. So 3 out of 8. Okay. In my mind, I was running through how I would tell you to get the number of permutations, and what you would do. I mean, how is it that it would be 8? But remember, you're tossing the coin 3 times, and you have 2 choices for the first, 2 choices for the second, and 2 choices for the third. So that's really not so much a permutation as the fundamental counting principle. So it's incorrect for me to use the word permutation because it's a counting. You're counting out the sample space. So 2 times 2 is 4 times 2 is 8. Okay. All right. Now it says you select a family with 4 children. If M represents a male child and F a female child, the set of equally likely outcomes for the children's genders is given. Because you can imagine that you have a firstborn son, or maybe you don't have your son until the third, or the order matters. We're always talking about birth order anyway. And so they list out all the different possibilities. And again, you can do that with the fundamental counting principle. You can have a boy or a girl, a boy or a girl, a boy or a girl, a boy or a girl. So you expect to have 16 total different combinations, which is what you have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now you want to find a family with exactly 2 male children. So you come through and count 1, 2, 3, 4, 5, 6, right? 6 out of 16. So we have 6 out of 16, which reduces to 3/8. Okay? So that's kind of fun. All right, now they're going to try it. They're putting the combinations and the permutations and the fundamental counting principle all together to help us work through some probability questions. So if your brain is starting to hurt, I'm right there with you. Okay, it says Tyrone, Kim, Sarah, Simone, Dawn, and Sergio and Maria have all been invited to a party. They arrive randomly, and each person arrives at a different time. Okay? In how many ways can they arrive? All right. Well, that's a slot problem. We can figure this out with the fundamental theorem of calculus. No, just probability or fundamental counting theory. Okay. So we have how many people? 1, 2, 3, 4, 5, 6, 7 people. 1, 2, 3, 4, 5, 6, 7. So, who can arrive first? Any of the 7. Do y'all agree? But now, somebody already arrived, so I only have 6 people to pick from. And then I only have 5 people, and then 4, and then 3, and then 2, and then 1. Okay? So the different ways is actually 7 factorial. So you come in here, you can do 7, you can type it in, or you can do that math and go over to probability and choose the factorial button if you want. Or you can just do 7 times 6 times 5, however you want to do that. And you should get 5,040 different ways that they could arrive. All right? Now, it says, in how many ways can Tyrone arrive first and Maria last? Okay, now we still have our 7 slots. But we're guaranteeing that Tyrone comes first and Maria comes last. So there's only one thing that we can have in the first slot. That's Tyrone. And there's only one thing that we can have in the last slot, and that's Maria. Okay? So if that's required, how many choices do we have for the second slot?
5.
Good. 5, and then 4, and then 3, and then 2, and then 1. Does that make sense? So this is really like the same as 5 factorial, but you can just type in 5 times 4 times 3 times 2 times 1. You don't need all those other ones unless you want to. So there are only 120 ways where you would have Tyrone first and Maria last. So like if you were in prison, this would be a fun thing to do. Like write out all the different combinations. Like actually write their name. And then you could actually say, this is right. There are only 120 ways where, because you could take a highlighter and highlight the... I say that in jest, but it's actually true that people who study probability, especially like probability of tossing, how do we know that there's a 50-50 chance that you toss a coin? Well, that you'll get a head or a tail. While it feels right to us, it actually can only be verified empirically, which means through experiment. And there were prisoners of war in World War II that were like statisticians, and like they're bored, so one of them flipped a coin like 50,000 times. And he recorded what he got, whether it was head or tail, and he actually did get about half the time he got heads and half the time he got tails. I don't know if you've ever done that with flipping a coin, but it could happen that if you did it, if you had a run of 10, you might get 8 heads. But the truth is, it's still a 50-50 chance the next time. But you just have to have a really big group in order for it to even out to 50-50. All right. Find the probability that Tyrone will arrive first and Maria will arrive last. Well, we found all the total outcome. That was the 5,040. And we found that there were 120 ways for Tyrone to arrive first and Maria to arrive last. So 120 out of 5,040 is the probability of that occurring. And you can reduce that by hand, or you can do it with your calculator. If you do 120 divided by 5,040, and then you can do a math frac button. Math, choice 1. So it's 1 out of 42 is the chance that Tyrone will arrive first and Maria will arrive last. Okay. So now we have a situation. 6 stand-up comics, A, B, C, D, E, and F, are to perform on a single evening at a comedy club. The order of performance is determined by random selection, and we're asked to find the probability that comic B will perform last. And we want probability. Okay. So that means we need to first figure out what our denominator is. What are all the different ways that they could perform? Well, we have 6 comics, and so that's 6 slots, right? And so we have 6 choices for the first comedian, then 5, then 4, times 3, times 2. I'm going to draw a 6th slot, okay? So this is the total possible permutations in this case, because order matters. Okay, and so we will come in here, and that's just 6 factorial, but you can type it in 6 times 5 times 4 times 3 times 2 times 1. So that's 720. 720. Now, what are the chances, or what's the probability that comet B performs last? Well, if it's the case that comet B performs last, there's only one way for that to happen, right? Comet B performs last. But if you've already made that happen, how many choices do you have for the first comet?
5.
You only have 5, right? Because B has to go last, so you can't pick from him anymore. And then 4, 3, 2, and 1. So it's 5 factorial really divided by 6 factorial. So if you do 5 times 4 times 3 times 2 times 1, you get 120. And if you're having a good day, you might see that since it's 5 factorial divided by 6 factorial, all you're going to have left is a 6 on the bottom. So this reduces to 1/6. But 120 divided by 720 is in fact 1/6 if you math frac that. Okay, so that is that one. That's the first answer. Okay, now what we want to know is find the probability that comet E will perform 5th and comet C will perform 2nd. Okay, so here's our comedian lineup. Comet E is 2nd, so there's only one way for that to occur. Comet E is 5th. Comet C is 2nd. And comet E is 5th. There's only one way for that to occur. So now, if that's going to happen, you only have 4 choices for the first comet, and then 3, 2, and 1. So now it's 4 factorial over 6 factorial, which is going to be 1 out of 30. Because this is 4 times 3 times 2 is 24 out of 720, or 1/30. So this is 1/30. All right, how about the choice C now? It says, or question C. The comedians will perform in the following order. Oh, okay. They give you the exact order. How many ways can that exact order happen?
1.
Good. So this is just 1 out of 720. All right, now comet F or comet A will perform 5th. Okay? 4, 5, 6. So how many choices do you have for the 5th slot?
2.
You have 2. This is either A or F, right? So how many choices do you have here for the first comet?
5. 4.
Good. It's actually 5 because you either picked A or F, and then the other guy goes into the pot, right? So he could be first. So this is going to be 5, 4, 3, 2, and then 1. And so that is that's 5 factorial times 2, right? But anyway, we do 5 times 4 times 3 times 2 times 1. Oh, we had 2 2s times 2. So that's 240 out of the 720. And that actually reduces to 1/3. You can probably see it. The zeros cancel and 24 goes into 72 3 times. Okay, here we are. Now, the next one says, we've got number 15. A group consists of 7 men and 5 women. 4 people are selected to attend a conference. In how many ways can 4 people be selected from this group of 12? So what are they looking for? 4 people from a group of 12. Is that a combination or a permutation? Right, it's a combination because this order doesn't matter, right? Okay, so we want 12, choose 4. So 12, choose 4. So you do 12, and then you do math, and then you go over to probability, and then down to combination, which is number 3, and then 4. So that's 495 different ways that you can select 4 people from the group of 12. Now, how many ways can you select 4 women from the group of 5 women? Well, that is 5 choose 4. That's a combination. So you can come in here, and you can actually just do second enter to edit this and change your 12 to a 5. And there actually are only 5 ways that you can pick 4 women from a group of 5. Okay, and so now the last question is find the probability that the selected group will consist of all women. Well, there were only 5 ways to get all women, and how many total ways were there?
400.
Right, so we're going to do 5 out of 495. But we can reduce this fraction. So you can do it by hand, or if you do math frac, 5 divided by 495. And then math frac is 1 out of 99. Okay? Let's play Lotto some more. To play Lotto, a person has to correctly select 6 out of 45 numbers. And they have to pay $1 for each 6-number selection. If the 6 numbers picked are the same as the ones drawn by the lottery, mountains of money are bestowed. What is the probability that a person with one combination of 6 numbers will win? Okay, well, apparently order doesn't matter. And so we have 45, and we're going to choose 6. So we do 45, choose 6. That's going to be all the different combinations of 6 numbers when order doesn't matter, out of 45. So we do 45, and then we do math. We go over to probability, and we're going to choose 6. So 8,145,060. Now, what is the chances that you bought one ticket and it's the right one? It's 1 out of 8,145,060. Yeah, not real likely. Not really likely. Well, say you got $100 in your pocket and you don't want to spend it on your girlfriend, and so you decide that you're going to go buy 100 lottery tickets. What are the chances that that you're going to now have the right one? Well, now it's just going to be 100 because you've got 100 different tickets, so it's going to be 100 out of that, which is still probably not a good choice. You can reduce this, and actually this one won't reduce in your calculator. It's such a small number. Watch. If I do 100 divided by 8,145,060, that is a scientific notation. That means move your decimal to the left 5 places. So this number is 0.00001. That's the chances. That's the probability. Not very likely. And if you try to math frac this, your calculator can't even give you that fraction, all right? So you have to reduce it by hand. Like, I think 20 goes into both of these numbers. So if I do 8,145,060 divided by 20, I get 407,253. And 20 goes into 105 times. So this is 5 over 407,253. It's kind of where you have to reduce. Yeah, it's a very, very unlikely that you're going to hit the lotto. It's not really worth trying to do that. I have a story though, and I wonder if you guys have stories probably, but when I was in graduate school, the lottery was just starting to come into play here, and so as mathematicians, we all would talk about it a lot. And I remember the statistician that was in our, he was a teacher in my class, at Baylor, and he said, just through passing, he's like, well, you know, if you always play the same numbers, you do actually increase your probability. And I'm like, how can that be? Because it seems like an independent event, right? It doesn't matter. It seems to me like it's just as likely that 1, 2, 3, 4, 5, 6 can come up on any day as many times, right? And he just said that in passing. And then a few years later, my uncle, who's in Australia, they love to tax people. My mother's Australian, so I have a lot of family over there. In Australia, they're big time. Everybody pays about 70% of their income goes straight to the government. And so the only thing that's not taxed, or one of the few things that's not taxed, is if you win the lotto, right? So my uncle, for 20 years, he and his wife played the same numbers on the same, like the Sunday and the Wednesday or whenever it was. I mean, and they spent probably over 20 years, probably $10,000 playing these same numbers. Even they went on vacation, he would have my grandfather buy the tickets. They always did it. And he ended up winning. And he won. Of course, he had to share it with like 4 other people, but he won like $500,000. Isn't that cool? But it was $500,000 Australian, but at least he didn't have to pay tax on it. It's still pretty. It just kind of, he still had to work and everything. It just sort of made everything in life easier. It's fun. Do you ever watch those shows where they talk about, when people get and they win it all and then how rough they have it?
What is it all?
What's it called? Or there's do you see those shows on like TLC or I just I feel like if I won $1 million, I'd be smart with it. Okay. Now it says a box contains 21 transistors, 4 of which are defective. If 4 are selected at random, what are the probability that you pick 4 that are defective? Well, first of all, let's see all the different ways that we can pick, 4 transistors. Obviously, order doesn't matter because you're just popping them in there, so it doesn't matter. So we're going to do 21 choose 4. And we can do that on calculator. 21, and then math. And then over to probability, and down to choice 3, and then 4. So 5,985. If you don't have a calculator, remember you can do that. You can do this as 21 factorial over 21 minus 4 factorial times 4 factorial. So if you don't have the graphing calculator, you can do it that way too. You'll get the same answer. Right now, this is your denominator. That's how many different combinations of the 4 that you can pick from 21. So what are the chances that they're all defective? Well, there's only one chance because there's only 4 that are defective, right? So that's just 1 out of 5,985. Now, to get the next one, it says none are defective. Okay? So what you want to do is kind of think of that. To get those number of ways, you want to think of it with slots. How many non-defective are there? How many good ones are there? Well, if there's 4 that are defective, there are 17 that are non-defective. Does that make sense? So the first one you pick, and then the second one, actually, I don't want to do a permutation. I want to do a combination. So I've got 17, and I want to choose 4. The reason I don't want to do a permutation is because the order doesn't matter. And so if I do 17, choose 4, 17, math, over to probability, down to choice 3, and then choose 4, I get 2,308. Okay, so that is the number of combinations of non-defective, not defective, all not defective. And so if you do 2,380 and you divide that by 5,985, that will be the probability that you select 4 that are non-defective. So if you do 2,380 divided by 5,985, and then you can math frac that to get the reduced fraction of 68 over 171. Okay, last question. It says a city council consists of 7 Democrats and 6 Republicans. If a committee of 4 people is selected, find the probability of selecting 2 Democrats and 2 Republicans.
0.
All right, now we are from this group. We're going to pick 4 from a group of how many? From a group of 13. Do y'all see there's 13 total? So our denominator is going to be 13 choose 4. That's how many different committees we could form. Some of them may be all Democrats, some of them may be all Republicans, etc. So 715. So we have 715 possible, this is the total possible committees, different committees, right? Because the order doesn't matter, so that's why we didn't do it in permutation. Okay, now, we want to have 2 Democrats and 2 Republicans. So of the 7 Democrats, we want to get 2. So that's a combination. 7 choose 2. So we'll come in here and we'll do, I can do second enter, and then I can just change this to a 2, and I can change this to a 7. So that's 21. There are 21 combinations of 2 Democrats. And if there's 6 Republicans, we could do 6 choose 2, and that'll be the number of combinations for the Republicans. So that's 15. So if we want a committee that has 2 Democrats and 2 Republicans, you want to put the number of ways that you can choose 2 Democrats, which was 21, and multiply that by the number of ways that you can choose 2 Republicans, which is 15. So that's this fundamental counting principle there. And that's going to be the total number of combinations that would be made up of 2 Democrats and 2 Republicans. So 315 out of how many possible? 715. So we have 315 divided by 715. And you can math frac that. Oh, I'm so sorry. I gotta hit the right button. I don't know if I hit the right button. And we get 63 out of 143. Does that make sense? So 315 out of 715 reduces to 63 out of 143. I found that one to be really tricky, but it was the idea because we had to use the fundamental counting principle at the end. Okay? So that's it.